We did the principal 1 plus r over n to the n t. Well, as this n approaches infinity, as n grows larger and larger and larger, this growth factor in here approaches e. No, that's scientific notation. That's the e. This is a different button. This is the e. This is 2.17 or something like that. So as that's how it's defined. That's where it came from. It came from an approximation as the n value, no matter what your rate is, no matter what, as n gets larger and larger and larger, it's going to approach this value of e. Like I said, it's like 2.718946443 I'm just making that up. But there's a great tutorial. It's where that compounding, remember how yesterday we had compounding interest where it was quarterly, daily, and so on? The more that your interest is compounded, the more that it approaches this. So what they call that is continuously compounding interest. And we'll go back to the word problems for stuff like that at the very end. There's this different formula as to a compounded certain amount of times versus a continuously compounded problem. It's very, very easy. So, E, like I said, it's this natural log. It's the base of the natural log. Don't have to memorize. It's 2.7 and change. Basically, remember, as n is getting larger and larger and larger for this setup, that's what it approaches. So as we get into, so what happens is we get a lot of simplifying with e in it. E cubed times e to the fourth. What do you think it's going to equal? Done. That's it. All of your exponent rules are still apply when it's e. You treat it the same way. Okay? You treat it the exact same way. Because e is a number. If it was 2 cubed times 2 to the fourth, it'd be 2 to the 7th. So it's the same deal. Oh, I didn't tell you guys this. I found this out yesterday. There's a, you know what they use prime numbers for? Or better yet, do you know what a prime number is?
Yes.
Yeah. You know what they use them for? Encryption. A lot of things are encrypted via prime numbers because it's hard. You can't divide things out. It's hard to figure out where you're how to break into systems. So what they do is they try to continuously one-up themselves to find the next prime number. These uber large prime numbers are completely useless, but they're just kind of cool because people are kind of nerdy. So what they did is they found the next prime number just the other day. It's 2 raised to the 74 million something 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 power, and then they subtracted 1. That is the now largest prime number out there. And if you put all these digits and wrote them all out, you would have roughly 23 million digits. What? Yep. And this is where it gets crazy. If each digit was only a millimeter wide, if each digit was 1 millimeter, this number written out would be roughly 13.5 miles long. Number after number, it would be roughly 13.5 miles. Do you guys know where the elementary school is on Plank Road heading out of town? North Grove Elementary? You go past the Jewel, past Casey's, and you go around that S-curve out there? Yeah. From here to there, that's 12 miles. From here to Canelan High School, I don't know if you guys have been there, that's 15. So you start to get the idea of how far away 13.5 miles really is. And that's at 1 millimeter font. So normally your 10 font on a page is not a millimeter, it's a centimeter maybe. So that's a lot more. Just thought it was kind of cool. You guys really don't care, do you?
No, I care. And that's insane.
Anyway.
It's just mind-blowing.
10e to the third over 5e squared. What do you think you're going to get?
2e.
Or not 2e is that the question?
I'm good.
2b or not 2b?
Shakespeare.
Oh.
Hark! In the upper window there is a glow. I don't know the rest of that verse. It's Romeo and Juliet, in case you didn't know.
I never read it.
They grew up and had children. You know that? Ruined the book for you, sorry. Same deal.
Thanks.
Just like Tom Sawyer and Huckleberry Finn drowned in a boating accident, so sorry about that one.
I think they're reading Huckman right now.
Yeah.
So
I actually like the book.
it's a good book. It's a really good book.
You get that. No, actually, they start pretty soon in like chapter 8 or 9. They start water skiing behind paddle boats. It's kind of cool. With the values of E, we also do some graphing. Graphing with E is very, very simple because what happens a lot of times, since E is an approximate value, you're only really using one or two numbers. You're usually finding your intercept and then going from there. Your H and your K stuff still works the same. You still have the same idea of directionality with curves as far as growth or decay with this stuff, and I'll show you how it works itself out. Don't write this down.
Got it.
Okay, done. Very good. Now, what happens here is that you get exponential growth when you have a base E, or you can have exponential decay if you have a base E as well. What happens is it depends upon the rate. Okay, the rate of whether it's positive or negative tells you whether it's going to be growth or decay. Now, when you're looking at it, you have your generic form of this. Y equals A times E to the Rx. Your generic form. Now, if R is greater than 0, growth. If R is less than 0, decay. That's really all there is to that. Now, what happens is you could still have an A value that's negative, so it could be reflected over one of the axes, but it's pretty simple to see these things. When we graph a lot of exponential growth, exponential decay via E, usually it's calculator based because there aren't any clean numbers. There's usually only one clean number that whole scenario, to be honest with you. Okay. So what you need to really understand here when you're dealing with E is that when you have Y equals A times E to the Rx, if R is greater than 0, growth, R less than 0, decay. Oops, helps if I know how to spell. And then the other idea is when you throw in an H and a K. If you throw in an H and a K, you're going to have X minus H plus a K. What do you think that K value is going to stand for again? No. Your asymptote.
Yeah.
You're still going to have your horizontal asymptote at Y equals K and going from there. Okay. It's a very, very simple thing to work with. We will use the values of E, log base E and things like that, natural log and all that next week, probably starting Thursday. Next Monday, I completely had forgotten, we have myself, Fontana, Lofthouse, Ms. T, Mr. Wascoda, Mr. Reyes. The 7 of us are going to be out because we have I think it's our last day for the new book for next year. So we're going to be out next Monday. So what I have for you guys right now is a nice giant review packet from 8.1 through all of 8.3. Come Tuesday, we'll go over all of it, see if there's any lingering questions. I got some extra word problems that are thrown in there for you. What I want to do then is next Wednesday is quiz over 8.1 through 8.3. That'll be calculator, non-calculator. Obviously, the non-calculator would be the graphing of exponential growth, decay things. Calculator would be the word problem stuff. It's fairly straightforward. Okay. Then on Thursday, we'll start with logarithms. They're big, they're heavy, they're wood. That's a Ren and Stimpy joke. Do you know who that is?
Yes.
Okay. So, yeah, they do, obviously. So what happens a lot of times when we graph these values with E, we're looking to figure out where they cross the excuse me, where they're crossing the the y-axis And then we're just trying to get one other point via our calculator. So if I have y equals 2e to the 0.25x, is this a growth or a decay problem?
Oh, 7.5, okay.
It's growth, and my a value is positive, so it's moving from left to right, increasing. What's the value of k in this case? 0. So where's my asymptote? 0. Is there any shift to this problem?
No.
No. So in and of itself, it's kind of like its own parent function. So I know that I'm going to have an asymptote at 0. What's my y-intercept?
2.
Very good. So what happens here with these things, if you're picking out where your y-intercept is, you're just going to pick out 0 for x. If you substitute in that, you're going to get 2 times, well, basically 1. Now, from there, it's a matter of picking another point. Usually what happens, you just pick the next number, 1 or 2 or something like that, and you just use your calculator to figure that out. Now, in the calculator, there is an E button, not the EE one, which you guys have probably used in chemistry.
Oh, I hate it.
Yeah, scientific notation.
I'm a beaver.
Yeah, I'm never a big fan of that. I always got it wrong. Second ln. That ln stands for natural log. That's how you get your e. So if we go 2 e to the 0.2 or 0.75 times 2, we'll use 2 as our next value, gives us a decimal approximation, roughly 9. Are we okay with that? So then I know that at 2, it was 8.9. And it's doing this. And there it goes. You have to do that sound effect when you're drawing graphs. And if it's falling, it's.
And where's the E button at again?
Second natural log. ln. It's the third one on the left from the
Oh,
bottom.
I got it.
Oh.
Yeah. Okay. Everybody get that okay?
Yep.
Okay, that's kind of how you graph these. Okay, so let's talk about, yes ma'am.
So you just want the y-intercept from one of the points?
A lot of times when we graph E, it's going to be a y-intercept and the horizontal asymptote you'd be looking for, because it's not an easy value to be able to substitute in and get normal numbers. When we do logarithms, it's going to look really, really weird, but you'll be able to get at minimum 2 points on a logarithm graph using non-calculator. Graphing E, you kind of have to.
So is A the horizontal asymptote?
No, your horizontal asymptote would still be that plus K. So since there's no, your plus K here is 0, that's where we got that. Okay.
So K is the horizontal asymptote?
Yes, sir.
Okay.
Just like it was with the exponential growth and exponential decay.
Okay.
E is growth or decay. It's still exponential growth, exponential decay. It just so happens the value of B is when that it's the 1 plus the rate over n is getting very, very large. So let me show you guys what happens when you talk about what's compounding continuously. Like I said earlier, the principle when you have that 1 plus r over n to the nt, that's your compounding interest style problem. And as I said, as n gets larger, as n approaches infinity, it's compounding continuously. It approaches this value of e. So this is where the PERT comes in. It's not because you have dandruff. PERT.
Yeah.
It's P, E to the R, T. Where P is your principal, the initial amount again. E is the button. R is your rate, again, as a decimal, your percentage as a decimal. T stands for time. So you'll be able to tell, one question's always come up, how do I know if I'm using compounding continuously versus compounding quarterly? Well, it'll say it's compounding continuously, or it'll say I'm compounding quarterly. So if it says continuous, you use E. If it doesn't, you don't. That's about as difficult as this gets.
Sweet.
Yes, like I said, this is a lot of new material, but the material itself isn't very crazy. Logarithms are usually where things get a little messy. First half is pretty simple. Okay? Should I give you an example?
Yes.
You deposit $1,000 in an account that pays 8% annual interest, compounding continuously. What is the balance after a year? 1 year is boring. Let's do it after 12 years.
16.
All right, 16 years. You put $1,000 in a bank account for your kid that when they're born, and after 16 years, they get to use that money to help themselves purchase a car. Real world application. So what's your principal amount?
1,000.
So we have 1,000 e to the 0.08 times 16. $35, 96, 64?
Would you round it?
I messed up somewhere.
Usually. I depends on the bank.
terms of like,
Yeah, usually still round to 5. But then it depends upon the bank.
or put point. That's what I messed up.
You get.
I put 0.8 and not point.
Oh, I wish I got 80% return on investment. Man, that'd be awesome. 8% ROI. Man, that'd be sweet. Well, if you think about it, you guys know what a commodity is? When you're talking about stuff in terms like of building trades, commodity items are things that are used in every single building. 2x4, drywall, things like that. So when they say commodities, those are your standard things that you use for, usually for when you're building stuff. Now, commodities are usually sold at stores, like Menards, Lowe's, Home Depot, things like that. They're usually sold at a cost that the person that's selling it is losing money. You normally do not make any money on selling commodities. You make money on stuff like the nails to hold the 2x4s together, the drywall mud that you use to seam the joints. What happens is, if you start to look into what things actually cost versus what they're being sold, there's what, like, you guys heard of markup before? All right. If I'm going to, let's say you're going to do a lemonade stand. You buy fresh lemons for 10 cents a lemon. You got them at Aldi. You bought 100 of them. Okay, so you're out $10 right now for material, and you bought a couple jugs of water. So let's say you're out a total of $15 for your lemons, for your water, for some sugar, for some cups. Now, if you're going to sell this stuff, you want to make your money back, and then some. I'm hoping, right?
Yeah.
You just want to give away free lemonade. It's nice, it's a very nice gesture, but you don't want to do that. You need to figure out the cost at which you make money. You want to maximize your profit. Ooh, look at that again. We did those maximize things last semester. It's the same basic idea. Commodities, when you have a commodity, it's sold at a percent, it's usually sold at an extremely low markup, if not loss of money, because they're anticipating that if you're buying 2x4s, you need to buy nails or screws. If you're buying drywall, you got to buy the mud and the tape to put it together. Things like that. Does that make sense?
Yeah.
So it's also kind of like the same idea when you buy a car. Oh, do you want the floor mats? They don't give you floor mats in a car. You don't give me a little things like that. It's the add-ons. It's the add-ons where people make money. That's how it works. Yes, ma'am.
Is it kind of like, I don't know, like, if you go to a bar, then they give away like free popcorn, like if you can buy one.
It's true. It's exactly right. It's exactly right. Because what a lot of times in places like that, if you're in restaurants that have free food, that stuff that's out is usually extraordinarily salty, because it wants you to have something more to drink. And if you think about, you bring up popcorn, a movie theater. Do you honestly think a bag of popcorn is $12?
No.
No.
But it is there.
It is there, and that's where they make all of their money. They don't make any money on movie tickets. They have to pay for the movies to be in the theaters. They probably make, if they're lucky, they might be making $1 per ticket. they're making their money on the concessions. It's like that in any business, if anything like that. When you're a captive audience, you go to a ball game. Does a hot dog really cost $7? No. But you're a captive
Water
audience.
costs like $3 up there.
I know. So that's why, you know,
And
when you
they don't
go
even
to,
give you a cat ring.
yeah.
Like, I don't understand that.
So that way you're not refilling it and walking around with it.
So,
It's smart on their part, but and now even at Bears games you can't have a backpack anymore. Whereas you go to a Cubs game, you can still carry a backpack, a small backpack. When I took Connor to a Cubs game last year, we always bring sandwiches and a bag of chips and stuff like that. Saves you $20 at the concession stand. So anyway, like I'm talking about this, really the only thing you guys have to be careful with when you're dealing with compounding continuously is if it says it's compounding continuously, you perk. If it doesn't, it'll say it's compounding quarterly or something like that. You have to go to the other formula. That's really all there is to this. Yes, sir.
So you don't use E when it says compounding continuously?
E is when you are using compounding continuously. If it says you're compounding quarterly or daily or monthly, that's when you use that 1 plus the R over N. That's the only difference. This formula is only for compounding continuous. Okay? That's really all I got on this stuff. It's pretty quick. I'm gonna have you graph these things, you think? No, but can you put that in your calculator, figure out when to estimate the number of endangered species when it reached 1,000? Let's try that real quick. Just use the table function the exact same way as we did yesterday and the day before. So you have 119.6 e to the 0.0917 t. So that's your list of endangered species. So the initial amount of endangered species was 119.6. Seems weird. Maybe it's supposed to be in the thousands. I don't remember when I cut that off by mistake. Where T is the number of years since 1972. So what's year 0? 1972. What was the number of endangered species in 1972? Maybe it was a salamander missing half its tail. Because in 73 it grew back. Salamander tails, they grow back. You guys really must hate me.
No, that's not.
That's half.
It's half of it, it's 0.6 of it. So, estimate when the number of endangered species reached 1,000. So,
After 23 years.
after how many?
After 23 years.
After 23 years, so you'd say roughly, what, 1995?
Between 95 and 96.
Okay, does that make sense? Do those, please and thank you.
You're welcome.
Wow, this is nice.
That's weird doing this in the dark like that.
Yeah, why are we here?
I don't know. I was watching that great video. Letter E, letter E, letter E, letter E. There will. I can't sing.
There's
Yeah.
Neither can I.
You should just stop where you're.
It's a good song.